Our first talk today is from Britton Smith. Britton is an astronomer at the University of Edinburgh, the Royal Observatory of the Edinburgh seat of Arthur's something. Anyway.
Not quite that complicated, but that's about right.
Okay. All right. So Britton's going to be giving us a talk about YT for merger trees.
All right. Hi, everyone. Thanks. I just want to talk about a little project that I've built called ytree. And I think the best part about it is I feel really clever that I made up the name ytree. So much so that I went through all the headache to change the name from something that was much dumber in GitHub and all that stuff. So if you're not familiar with cosmology or galaxy formation or things like that, we know that through a process of hierarchical structure formation that halos they grow from very small things into larger things by merging with each other. And this is all because the primary force of structure formation is gravity, and the attractive nature of things causes structure to build up in this way that can be best visualized by a tree. And so here is just an example of that, where the top right is some object or some dark matter halo at some final redshift. This is actually at say the current day, and all of the dots before it are its progenitors, and the primary progenitor of the halo is shown in red. And as we step backward in time, as we go down. All the other little black circles are other progenitors, other objects that have merged into this thing. And the size of the circle is sort of proportional to its mass. Like basically the whole reason that YT exists is that there are lots and lots of merger tree codes out there, and they make lots of different file formats. And if you want to actually do something that uses more than one, or you want to share analysis or anything like that, you need a common library to do that. And that was the whole reason that I started to work on this project, basically taking inspiration from the raison d'etre of YT in general. So here are just a few examples of different merger tree formats that you can see out there. Lots of different file formats, lots of ASCII formats, file formats where properties of the halos come in halo catalogs, and then the properties of the merger trees come in separate catalogs. In the consistent trees formats, everything is, all of the trees are in these large sets of ASCII files. Halo tree, which is the one used for by the Illustrious project, are these formatted binary files. There's lots and lots of different ways out there to do this. And so ytree is trying to solve the same type of problem as YT, but just for merger trees. Using YT or ytree should be, well, I've designed it to be as familiar as possible to the experience of using YT. So you import it, and then you would load a merger tree data set, which I'll call an arbor here, simply with ytree.load. That's designed to be very, very similar. Okay, so I've loaded it, and then I have all sorts of descriptive attributes associated with it, like the Hubble constant, other cosmological parameters, the box size, things like that. And as you can see, the box size here is represented with units of megaparsecs per H, because under the hood, we're using YT and unit for doing all of that stuff. Similarly, we have a field list, which shows the available fields in this data set that we can query. And these are all the things on disk. So an arbor, the thing that we just loaded, is meant to be considered a collection of trees, or at least my wife told me it was defined that way, and I only later found out that's not really true. But you know what, it sounds very tree-like, so let's just go with that and never look back, right? So you can access all of the trees that you've loaded through this arbor object, which is basically meant to be like a data set object in YT. And at load time, very similar to YT, we do nothing but load and read the metadata. And we save all the expensive stuff for whenever you actually want it. So we can simply get the number of trees by getting the size attribute on that. And then and only then will we actually do the heavy lifting to figure out how many trees are in this thing. And then we can access fields for the root of every tree simply by querying them in a dictionary-like manner, just like we do with YT and data containers. And if we query, for example, the mass field on the arbor itself, we're going to get the masses of the roots of all the trees in the collection. And so I can use this to very easily pick out the most massive halo in the collection of trees. And so I'll do that, and I will just grab it like that. And now I have this myTree object, which is the most massive tree in this collection. And I can print things on it. I can now query fields just for that tree or that node. So that thing that we get back is what's called a tree node object. And I'll explain what that means in a minute. But basically, it's a halo in a tree that can be created on demand. And that halo represents the root of the most massive tree. And there's its mass, and there's its redshift, so on and so forth. I can get all the trees from the arbor just using array type slicing. And I'll get something similar. So there's the virial radius of the first tree. And so a tree is just a collection of these tree node objects which are linked together. So I'll again oops, I wasn't supposed to do that. Let's go back. So here I take the very first one. I'll print out, that's just this tree node object. And every one of these has links to its ancestors and its descendants. So here I'm just going to get its ancestors, and I will make that a list because all of these are done with generators. So myTree.ancestors will give you a generator that you can iterate through to get all of your ancestors. This halo happens to only have one ancestor, but then I can also get those ancestors' descendants. You can see that my ancestor's descendant is me. And given any tree node object, every tree node represents the root of its own tree. If you can just think back to that visualization there, every tree node has descendants and ancestors. Only the very root doesn't have any additional descendants, right? And so I can just in the way that I accessed the fields, like the mass and the radius of a given tree node, I can access all the nodes on that tree in these following ways. By using the tree keyword, I'll get all halos in the tree where any given tree node that I'm using is the root. The forest is all halos in the forest. And the difference between a tree and a forest is simply that a forest may contain more than one root in it. And this is used to look at things like flybys, where a halo may be only temporarily part of a larger tree. And then I can use this proj keyword to get only the main progenitors of the current halo. If you think back to that original image I showed, those would be the red ones, right? And so again, these are all done with a generator. And so that's why I cast this into a list, and then I can get the length of that here. And so I see there are 83 halos in this tree, and the line of progenitors has 48 halos in it. Now, similarly, I can access all of a given field for all of the
5 minutes, and then 5 for questions.
All right, thank you. So similarly, I can access the fields for all of the progenitor halos and so on and so forth by including both the proj or tree or forest keyword with a field name and get simply all the virial radii for all of the progenitors in the list. Also, like YT, I can create derived fields just from a simple function. So here I'll create the gravitational potential field, which is just the ratio of the mass to the radius times the gravitational constant. I define my function. I do an add derived field. I supply some units in that function. And then now that's immediately available to me. This is all just like YT. That's the whole point. Now, one thing that's a bit different from YT, we have something called analysis fields, where often you want to really compute and plug away at a given halo and store some value that is the result of far more complex analysis that may actually use YT to load the data set that this halo is living in. So I can add an analysis field, I can give it units, I can give it a data type, it doesn't have to be a float, and I can give it a default value. And then I can loop through all of the halos in my tree, and imagine this np.random is actually some very expensive analysis. I'll run that, and then now when I print them out, I can see here's my new field for all of the halos in this tree. I can also then resave these data sets to a slightly more optimized format. So the reading from these ASCII files is often quite slow, but ytree comes with a native format that is a bit faster that uses YT and HDF5 under the hood. And so I can resave them and load them just as I would before. I don't even have to load the whole or resave the whole arbor. I can load, say, just one or a collection of trees. And so I will save just the one tree that we've been working on. And now we can see that that TEDS field that I made has been saved along with it. And one of the nice things that you can do is all these additional fields will be saved to separate sidecar files. And that allows me to do this over and over. I can save and save and save and save and save and just keep adding to the sidecar files without messing with the core data of the original fields. We also have some canned visualization. We can make tree plots, and these can be highly customizable because you can supply functions to customize the appearance of the nodes and the edges of the tree. And there is a lot more information on how to do this in the docs. The future of this, at least the things that I want to do, as always, if anyone has anything else they want to add to this, I would love to take contributions. These are the things in my mind. I will have ytree interface with YT and actually load the saved data sets as YT data and use the cut regions to do database-like selection on the merger tree data sets. So we'll have, a SQL-like language to describe, I want all the halos between these redshifts or in this mass range. And we'll use YT to do that under the hood. I intend to parallelize it using Dask. Currently, you can make a lot of these operations parallel simply by using YT parallel objects calls. And in my own analysis, that's how I sort of run things in parallel. But I'd like to actually parallelize the library itself. And there are at least a couple new front ends that I've got on my radar, the Velociraptor front end and the Moria front end by Benedict Deemer. But if there are other file formats out there that you use that you'd like to see integrated, I'm happy to either work with you or even do most of the lifting if you're interested in using this. Here are the resources for looking for this documentation and the source code, et cetera, et cetera. And so I'll just end by saying, I think I have the YT project as a whole to thank for inspiring me to try to build things that can be useful to other people. So thank you very much.
Wow, you ended with exactly 0 seconds left. That was impressive. We have time for a couple questions for Britton. Let me, oh, I don't have my participants window open. One moment while I view that. All right. So Maxime.
Thanks. So apart from support from other code, I'm mostly have a question like how much of the cosmology part is baked into this? Like if you have a collections of clumps that are not halos, but like clumps in a galaxy, for instance, or clumps like the one that Stephanie and Ricardo mentioned yesterday or the day before, would it make sense to be able to do that kind of analysis with it or to support it with ytree in the first place?
Yeah, sure. I think you could absolutely do that. The cosmology stuff is very loosely very loosely tied on to the end, and non-cosmological tree-like stuff is definitely possible. I've thought of similar things for doing fragmentation of collapsing gas, which goes into a tree-like structure. I played around with it a little bit, but I haven't done much. But I think it would be a very appropriate thing to try to do here, and I'd be happy to work with anyone who wants to do it.
Thanks.
Thanks for your question. That's a good question.
Clinton, did I do that okay?
Yeah. What do you want to say? Sorry. Oh yeah. So currently you can only load already built trees, right? There's no support for like building the tree directly.
So they're not specifically in this code. There is a separate project that used to be a part of ytree for making murder trees from YT Halo catalogs. And I pulled it out just because it was only sort of half baked, but it lives on and just needs a little bit of attention. And it can, ytree can still read in the format that it generates. So I do have a project that was reasonably mature, but just not getting the attention that it deserves. So it lives in a separate repository in the ytree domain. But it's very YT under the hood.
Okay. May I ask a second question, if or?
Yeah.
So second question is also it's a bit more. Oh gosh, I was going to say it's more a remark, and then I sound like all these annoying people at conferences that say, oh, that's actually more a remark. But anyway, do you know Tangos? Because Tangos is also a way to like analyze Halo catalogs, and I think there are it's already implemented like querying data from directly the simulation, as you said you wanted to do, except it's based off by n-body. So I guess if you want to implement that, that's probably one way to I mean, it's already been done, so there are probably good ideas of how to do it.
Sure, I'd love to know more about that.
All right. So it looks like we have exhausted all of the questions. Shall we move on to...